We can start. So welcome everybody again to this now fifth online seminar of the IAU G2 Commission. This is about massive stars as usual. And today is a real pleasure for me to introduce Alex David-Uraz. I still remember when we met the first time. This was in 2011. It was in Lactero. And he was just a very young student being part of the log. And I was amazed how he was doing the work. He was doing amazingly. And I understood that he was going to be a real promising researcher in the future. So it's very good to now being able to introduce this talk by Alex more than 10 years later. By that time, he was just finishing the master thesis. He did it in Université de Montréal with Tony Moffat, and then later joined Queen's University to do the PhD with Greg Bade as part of the MIMES collaboration, I can guess. And then after a few years working hardly on the PhD, he became a postdoc in several institutions across US, for example, Florida Institute of Technology, and then Howard University. And actually, presently, he's assistant research scientist in Howard University, but working at NASA, no? So you are kind of perfect. So his research interest is basically stellar astrophysics, and more specifically, the study of the outflows, the winds, and the interaction of these winds with the magnetic fields in massive stars. And he is mostly interested in understanding the characteristics and the drivers both of the small and the large scale variation that affect these stellar winds. Since 2018, more or less, is co-leading the MOBSTER collaboration. That is one of the important collaborations on the massive star community with 60 members from more than 50 countries. And he's leading together with Coraline Einer and previously with Jami Sikora, and now with Dominic Baumann. No? Recently, Dominic has taken this role. So I'm really looking forward to enjoy, as I hope all of you, the seminar by Alex. So floor is yours, whenever you want.
Great, thank you so much, Sergio, for this this really nice introduction. I do remember meeting you in Lactero, and I'm also glad that all these years later we're still able to collaborate. So thank you, Sergio, also for inviting me. I would like to thank the entire G2 Commission Executive Committee. It's a real pleasure to be talking to you today about multi-wavelength studies of OB stellar variability. Okay, so here we go. Okay, please don't be intimidated. I know that I have already a plot on my first slide, but as you'll see, this isn't to introduce a concept. So here we have a picture on the left from ALMA that's showing us kind of a collapsing cloud that's forming stars. And in particular, if you look on the right, we also have the identification of some pre- and protostellar cores. And so this is just kind of illustrating fragmentation. As we all know, OB stars are believed to basically all form as binaries or multiples. And of course, this is something that has a really important influence on the rest of their lives. And so very much like that's the case, I feel like as researchers in the field of massive stars, there's a very similar scenario going on. So the research that I'll be presenting today, the line of inquiry that I will be presenting did not form in isolation. Of course, it's quite tributary of, I don't know, maybe the surrounding massive stars that the region in the first place. So those are my advisors over the course of my career so far. So as Sergio mentioned, Tony for my master's, Greg was my PhD advisor, Veronique and Maurice were both postdoc advisors. Maurice is my current advisor at NASA. And so, of course, I owe them a huge debt of gratitude. But of course, there's a lot of other people. So here are just some of the usual suspects that I've worked with over the course of the years. But of course, there's many, many more. And a lot of the work that I'll be presenting today was made in large part in collaboration with these people. All right. I'll just start my talk also with a quick disclaimer. So despite my very lofty title and abstract, this is not meant to be some sort of unbiased review. Actually, it's very much biased towards the things that I'm interested in. And so I will have undoubtedly left out really important contributions and interesting results. As a result, I would like to extend a heartfelt Canadian sorry to anyone that I might have omitted in this talk. And actually, if that's been the case, if I forgot to mention your work, or if you would like to highlight something, please feel free to do so in the questions. And even better, if you think that we should collaborate on things, then I'll be more than happy to have you reach out to me. All right, so, oops, yeah, I keep forgetting that I can't change the slides by clicking. Sorry, that might happen a couple more times. One thing I'll highlight is that, of course, it's kind of nice to be addressing the massive star community. It's always nice to address everyone, of course, but usually my talk starts with a couple of slides kind of, justifying our existence. Massive stars are important because of this and because of that, and trying to connect to other fields. But thankfully, in this case, I don't think that I actually need to do that, because I think we're all quite passionate about massive stars. So I'll kind of skip that part and won't have to talk about compact objects and those sorts of things. All right, so let's get started. And one thing to note, and one thing that I hope will be a take-home message today, is that obviously massive stars are a little bit like, well, me and my emotions, but also like onions. They're quite complex, and they have many layers that are hidden under the surface, despite looking kind of like just simple objects. So let's start by drawing a massive star. Well, of course, we know that they possess a convective core, and surrounding that convective core is a radiative envelope. And because of that, relatively simple radiative envelope, for many years, massive stars were considered to be much more simple objects than their low mass counterparts, at least in terms of their visible manifestations. So everything we can see typically is linked to the surface. And so they were expected to be kind of these quiet giants just doing their thing. Okay, well, let's go back to the days of early UV astronomy, and here what we're seeing is a sounding rocket that was used in the 60s by Don Morton to acquire the first ultraviolet spectra of massive stars. Now, for astronomers of my generation and younger, I think that the image that's shown on the right makes us very, very grateful for the evolution of technology since those days. So these are the earliest UV spectra that were taken of massive stars. And we can see some line identifications here. But the main thing is that there are some lines that presented important emission and so-called P Cygni line profiles. And so early on, it was realized by Don Morton that this was actually something that was indicating mass loss. So basically, we have material being shed from the surface of the star in the form of a continuous wind. Okay, well, within a few years, we started gaining a bit more of a theoretical understanding of how this could happen. And the scenario that was proposed was the line driving mechanism. So basically, you have resonance scattering, and the cumulative force that occurs from that resonance scattering, that's from an ensemble of iron-like lines, can lead to enough momentum to basically shed the outer layers of the star. And in doing so, we have kind of this continuous wind. The one reason this works, so if you quickly saturate your lines, what helps you here is that you're actually accelerating the wind outwards. And so as you're driving your wind, you actually Doppler shift the wind material to regions that now have available photons. And so that's what allows you to keep driving the wind and keep driving it until you're able to completely launch it. Okay, so back to the drawing board, we now need to add our dense, strong winds to the picture of massive stars. Okay, still nothing too too variable or unstable. Except, as it turns out, when you get high resolution spectra of these stars, so this was from the International Ultraviolet Explorer, you actually start seeing weird features in the absorption troughs of these stars. So here is the silicon-4 doublet for HD 175876, and we can see the line centroids are indicated by these two lines at the bottom. And within the absorption troughs, the large extended absorption troughs of these lines, we actually have this pair of components that occur at the same velocity respective to the centroids of the two components. And so this superimposed narrow absorption is actually found in most stars that you'll look at. So if you have a massive star, a massive OB star that has a wind that's powerful enough to provide you with good optical depth, but not too powerful so that it completely saturates the line profile, then you're actually able to detect these. And the study by Howard and Prinja at the end of the 1980s showed that roughly 97% of stars in which you could observe this show it. So the basic idea is that it's ubiquitous. But in order to understand where it comes from, what really pushed the field forward was good time series of ultraviolet spectra. And so once you actually look at the time evolution of these structures, you can kind of form an understanding of what's going on. So here we have what we call a dynamic spectrum of UV resonance doublets. And the grayscale here, on the y-axis, we've got time, so time evolves upwards. On the x-axis, we've got wavelength or velocity space. And we can see that these features first appear at lower velocity and then extend to high velocity, high blue shifted velocities. And as they do so, they get narrower and narrower until they get very close to terminal velocity. Now, this exact sequence is very indicative of a structure in the wind. And in particular, the scenario that was found by Cranmer and Walke in '96 was that this could correspond to large-scale wind structures that arise from co-rotating surface spots. So the general idea here is that you have bright spots at the surface of the star that locally drive an enhanced wind. And this propagates into the sort of spiral structure that you see here as the star rotates, kind of a garden hose effect. Now, just to think a little bit about how that could lead to the sort of feature that I just showed you, let's place an observer to the right here, and let's focus on the column density that is between the stellar disk and the observer. So at first, this line of sight intersects this large-scale structure, which is called the co-rotating interaction region, or CIR, very close to the star. And as we know, the wind is accelerating radially outwards, which means that close to the star is a low velocity, whereas as you're getting further and further away from the star, you're going to higher velocity. Now, as the star rotates, what you notice is that the line of sight intersects the CIR further and further away, and therefore that's why you see your absorption component slowly drifting to higher and higher velocity. Now, in order to understand this, another thing that's important, if I go back to this picture, one might naively think that this is mostly a density effect, right? Because you've got these kind of overdense regions in the center of the CIR. But in fact, it's mostly a velocity effect. So it's the accumulation of material all at the same velocity that allows you to reach much higher optical depths at that specific velocity. And so the way to understand it in terms of how the structures form is that imagine that you're a little parcel of material being launched from the surface, and you're being launched from one of these bright spots. So at first, the bright spots occupies most of what you see from the star, and so you get all of that extra line driving from it. But then as you get further and further away from the star, the spot actually gets smaller, and the surrounding region does not provide as much driving. So you get less and less acceleration. Now, in this very simple cartoon, I'm not even including rotation, right? So as the spot kind of rotates towards the limb of the star, there's of course a projection effect. So this all adds up together to say that you're getting less and less driving. And at some point, you fall into some sort of coasting solution, and you've got material that's accumulating at that speed. At the meantime, you also have material that's being launched from the rest of the surface that's now crashing into you, and you just gather it like absorption. Now, in terms of the physical origin of the bright spot that can lead some ideas that pulsations could be seen in some of the stars that exhibit these structures. So in this case, I think we're seeing a dynamic spectrum in the optical of Xi Persei, which was inferred to have non-radial pulsations. However, there's a very important caveat with this particular hypothesis, and it relates to timescales. So as noted by de Jong et al. In 1999, any such pulsation by itself is unlikely to be the cause of the cyclical wind variability in these stars because the period is too short. I should also actually highlight something that I forgot to say, which is that this variability is cyclical. So when we look at these absorption components migrating in the dynamic spectra, they seem to do so on a timescale that's compatible with rotation. But if you try to phase these over long periods of times, you're actually not able to phase fold them. So what you find is that actually, there's a characteristic timescale, but the variability itself is cyclical. Okay, now the other main hypothesis that was offered had to do with stellar magnetism, which kind of foreshadows the second part of my talk. And we performed a study back in 2014 to try to get very precise magnetic measurements of some known stars that had very good time series in the ultraviolet. And what we find is that on the y-axis, we have roughly the field strength, and on the x-axis, we have more or less the wind momentum. And dynamically, it's very hard to see any strong influence from the upper limits we obtained on the magnetic field. So these are all non-detections. But if we infer, what kinds of fields could exist on these stars, we find that they're not likely to have a very strong dynamical effect on the wind. And so therefore, it would be hard to try to form these structures as a result of these magnetic fields, if they exist. Now, another thing that was proposed was magnetic spots. So I'll get back to this, but our assumption when we did the study was that the fields were large-scale dipolar fields. But the detection limits are very different if you consider small-scale fields. And in fact, some early work from Cantiello and Braithwaite on the so-called subsurface convection zone showed that you might expect to form some small-scale magnetic fields. Now, the connection between fields and bright spots is that if you advect a field to the surface, let's say this is a field tube, so you assume horizontal pressure equilibrium across the surface, and the added magnetic pressure that's due to the field decreases the gas pressure locally. Now, this decreased gas pressure means that you can actually see deeper into the star because your photosphere actually occurs slightly deeper. Now, because of the temperature gradient in the envelope, this means that you're actually probing a hotter part of the envelope. And so therefore, this region here will appear as a bright spot. This is the contrary of what we see on low mass stars, for instance. And to zeroth order, we provided a very kind of, simple scaling as to what field strength might create what sort of temperature enhancement and therefore surface brightness enhancement. We'll get back to this convection zone in a moment because it's actually quite important. But the general understanding is that it arises from a bump in opacity that is due to recombination of iron-like elements at about 165,000 kelvins. So this changes a little bit our picture of the envelopes of these stars, where we just imagine them to be radiative, but there's actually some contribution of convective energy transport. Okay, now this idea that there's these bright spots on the surface also seems to be corroborated to some extent by other diagnostics. And so here we have some photometry from MOST, which was a very important precursor to our current day space-based photometers, and was a Canadian-led mission, basically a suitcase-sized telescope which was launched into space and performed some really nice photometry of massive stars. And so here we have a time series of Xi Persei, and we see all sorts of little variations. But as it turns out, you can find kind of a characteristic time scale to these variations. And this was interpreted to be surface spots, which are slowly changing with time. More observations of this sort were also made with Bright for the other canonical massive star Zeta Pup, and seem to point in the same direction. Well, this places constraints on the types of surface brightness spots that you have. And so back in 2017, we kind of repeated the Cranmer-Nowacki simulations, hydro simulations of the winds of these stars with spotted surfaces, but taking into account the photometric constraints that were obtained by Teina Ramiramanantsoa et al. Usually I have it better, but it's still early in the morning here in the US and I haven't had coffee yet, so I apologize for that. And so we use that as a constraint to try to derive more realistic CIRs in the winds, and then compute some synthetic UV line profiles from that. And what we see is that the structures that we obtain in the UV dynamic spectra are qualitatively and quantitatively consistent with what is observed in real stars. So we kind of have this unified vision now of how the surface to wind connection gives us some variability that can be connected both in the UV and in optical photometry. Okay, so now we have to revise our picture to include these large-scale structures in the winds that present as sort of spirals. But this is not all. So another diagnostic that seems to show evidence for these CIRs and for rotational modulation in general is X-ray light curves. So here we see the X-ray light curve of Xi Persei. So you can see this change that occurs. There's also changes in hardness, for instance, that occur over the course of the rotational cycle. So you might be wondering, okay, why are there X-rays from these stars? Well, the general idea is as follows. So first of all, X-rays were observed in O stars as soon as X-rays were observed in stars. So here we have an early observation from Einstein, which shows that 5 stars in Orion were detected in the X-rays and coincided with, or sorry, there were 5 sources that were found in the X-rays in Orion that coincided with massive stars. So very early on, this was understood to arise from the line driving mechanism and instabilities that are inherent to it. And so I won't go too much into the details. You can ask me questions later about this. But basically, nowadays, we have much more sophisticated simulations that show in 2D that you have all of this large-scale structure arising, and you have shocks consequently that occur, and the material becomes hot enough to produce X-rays. Okay, how does this play into rotational modulation? Well, our general understanding, so going back to a picture of these spiral structures, you have shocks that are embedded throughout the wind, but the bulk of the wind remains cool and can actually absorb a large quantity of these shocks, of these emitted X-rays, sorry. And so one might naively think that simply the varying column density and therefore the enhanced absorption occurring within CIRs could maybe explain that. And if we do a simple calculation, we see, okay, well, there might be some of that explaining what we see. We get roughly a 10% change, but we know that in some cases, the variations are actually larger than that. They can be on the order of 15%. And so this might not provide us with a full picture. So we have a few hypotheses as to how else you might modulate the X-ray emission in winds that have CIRs. So one that's kind of obvious is as the wind comes crashing into the receding edge of the CIRs, when you have that velocity kink, you might actually produce some soft shocks. So there might be kind of X-ray emission being formed all around that boundary here. Another more subtle effect on top of the added absorption within the CIR is that you might actually inhibit the instability within the enhanced density of the CIR. There is some evidence for that, for instance, in the ultraviolet line profiles, because as you're creating shocks, you're creating a little bit of a turbulent velocity component. Usually that creates broadening. But as you'll remember, when the absorption got to very high velocity, it actually narrowed quite significantly. And so if there was an important turbulent component to the velocity at that point, you would expect much broader discrete absorption components, which is not what we see. So we have three possible suspects. We've got enhanced density creating enhanced absorption. We've got increased X-ray emission at the receding edge of the CIRs, and we've got inhibited shocks within the CIRs. So right now we're testing with PhD students in Montreal, Guillaume Lenoir-Craig, to try to get some new simulations of these CIRs and test all of these different hypotheses to synthesize X-ray light curves and X-ray spectra and try to see if we can explain this. Okay, now this embedded wind shock scenario also allows us to diagnose the winds themselves and their bulk properties. So here's just kind of a cartoonish picture of what happens. So you've got all of these shocks occurring throughout the wind. You've got this kind of two-component plasma. So you've got the hot plasma that's formed locally on small scales within the shocks, and you have some sort of filling factor that arises from that. And you've got the surrounding or the the bulk of the wind that's once again mostly cool and can absorb a lot of that X-ray emission. Now, if you imagine that you're an observer here on the right, of course, that's going to lead to some asymmetries in the line profiles, because if you look at the hemisphere that's towards you, so the wind is coming in your direction and is the blue shifted, so the shocks actually have to the X-ray emission from the shocks has to go through less wind material to get to you compared to those from the back hemisphere of the star, which is red, where the wind is redshifted, and where the X-ray emission has to go through much more wind material before it can actually reach you, which means that you expect to have redshifted absorption, and this kind of skews your line profile. So here we see for a variety of wind velocity solutions and characteristics of the filling factor, how the profiles that are closer to the center are actually at lower mass loss rates. But as you increase the mass loss rate, so as you increase the total amount of material that can absorb your X-rays, you start having these more and more asymmetric line profiles. And so this can be a very powerful diagnostic of the bulk properties of the winds. Now, this was used quite interestingly in the case of Zeta Pup. So we have Chandra observations that dated from cycle 1, and there was a much more recent campaign in cycle 19 that obtained really, really nice observations of Zeta Pup. And so by using an ensemble of lines, you can really get kind of a good handle on your wind properties and get fairly stringent fits on the mass loss rate that you expect from these stars. Now, the surprising thing here, and something that I do want to highlight quite strongly, is that between cycle 1 and cycle 19, so we're talking about roughly a difference of 18 years, there appears to have been an increase of about 40% in the mass loss rate if we take this modeling at face value. So this is quite significant, and this hints at timescales of variability that we might not have been aware of previously. So I know that already there are some important uncertainties in the determination of mass loss rates and wind properties, which play into our evolutionary models of these stars. But on top of it, there might be some secular changes occurring on timescales that are much smaller than the evolutionary timescales that we usually consider. And so this might be an added uncertainty that we need to take into account. So more observation of this is obviously warranted in trying to understand what's going on here. There have been some alternative scenarios that were proposed. So for instance, I think a recent paper by Gunderson et al. Argued that rather than overall change in the mass loss rate, it might have to do with changing shock properties, which in and of itself is also quite interesting because it points towards changing physics in the bulk of the wind. So however we look at this, this is something that we should definitely aim to better understand and get a much larger sample of stars for which we see this. Either Zeta Pup is a freak and this is an isolated incident, or this is actually something that happens in more stars and we need to really get a grasp on it. Okay, so this adds to our evolving picture. So now not only do we have all of these shocks occurring, maybe they're inhibited within the CIRs, but we're starting to have a much more dynamic picture of massive stars in general, and in particular their outflows in this case, but also their interiors, because if we had this subsurface convection zone, of course, this introduces once again another velocity components that can then perturb the surface as well. That may also play back into the perturbations that create co-rotating interactions regions in the first place. So we're starting to get this very complex picture of the interplay between the interior, the surface, the wind, and we're getting variability galore across the electromagnetic spectrum as a result. Okay, so as I just mentioned, another hypothesis that might be able to account for surface spots is the presence of non-coherent oscillations that propagate to the surface of the star and could create short-lived brightness spots or prominences or these sorts of structures. Now, this is evidenced in optical photometry as what is called stochastic low-frequency variability. And so how this manifests is basically an excess of what appears to be noise at low frequencies, but actually seems to potentially be astrophysical signal. So if we model this, we've got the white noise floor here, but there's an added so-called red noise component that can be fit that probably relates to the propagation of internal gravity waves to the surface. Now, there are several scenarios that are invoked as to the origin of these waves. So initially, I think they were predicted to occur as a consequence of convective core overshoot and gravity waves propagating from the core of the star. But then also there has been some increased interest in the role that the subsurface convection zone might play in generating and propagating these oscillations. Now, in both of those cases, an interesting thing is that you might expect this to be metallicity dependent. And so one project that we've got moving forward is exploring the role of metallicity in the incidence of narrow absorption components and large-scale structures in the winds of these stars. Now, of course, unfortunately, when we try to look at faraway stars in lower metallicity environments, it's much harder to get time series of the sort that IUE got for our galactic OB stars. But even snapshot observations, as we know, can give us some information. So there were some early attempts by Prince and Crowder to look at this in Magellanic Cloud stars. Of course, this was with slightly lower resolution observations, so it was a little bit more difficult to identify all of the features. But now we can benefit from the Ulysses project, which obtains a lot of HST data of bright stars in the Magellanic Clouds and even further environments that are at even lower metallicity. And an early look at some of the spectra of these stars does show the presence of NACS. So this is courtesy of Callum Hawcroft. So our project is going to be to look at the overall incidence of NACS within stars at lower metallicity environments, and this is an ongoing project. All right, so here I'm going to shift gears a little bit, and before we move on to the next section, I'll maybe take any questions you might have for the first section, because the second section will be quite different.
So if anyone wants to ask, just tell me in the chat. And
Okay.
Or if not, we can
It
go
doesn't
ahead.
seem like there's anyone, which is fine. I mean, you can also hold your questions till the end. So I'll just move on with part two. And in part two, well, we know that sometimes if we play with, currents and then maybe magnetic fields, then we might actually create monsters.
Alex,
Oh, yeah.
Dietrich has raised hand, so maybe you can ask if you
Yes.
want, Dietrich.
Yeah, please go ahead.
Yeah, thank you very much for this presentation, and which in many cases were reminders or were new to me. The stars that you have been talking about are supergiants. A very similar phenomenon is seen in BE stars, which have also been called co-rotating interaction regions. And that, of course, gives rise to the suspicion that the wind does not know what is at the base of the wind. This is decoupled, even though the influence of the stellar surface is important. And in BE stars, there is very strong evidence that the mass loss, the mass transfer from the star to the circumstellar disk is driven by multimode non-radial pulsation. This does not invalidate anything that you have been saying for the supergiants, but it probably serves as a reminder that several causes can have a very similar effect. Would you agree with that?
Yeah, I think that's a great point. I will, however, clarify that I'm not talking just about supergiants. So DACs are seen in OB stars across luminosity classes. But I do agree that there doesn't have to be a single driver, and that this could be kind of a more general kind of emerging property that comes from the wind. So I think that's a good point. And of course, one thing I'll note also, as I said, this is a very biased kind of presentation. I haven't spent a lot of time talking about pulsations, not only because it's not my area of expertise, but also because just for the sake of time, because I have to cover a lot of things. But of course, they're extremely important. And if we're talking about variability in OB stars, pulsations should definitely be kept in mind. So yeah, that's a great point. Thank you.
You were very clear about your bias in the introduction. That was very fair. Thank you.
Okay, good.
Okay,
and I see John has
you
a
want
question.
to ask a second question, and then we can go ahead. June?
Yes. Hi, Alex. So I actually had a question about the mass loss rate change in theta Puppis, which of course I'm aware of, and it's a very interesting result. Was just wondering if indeed this is due to a change in mass loss rate, or more generally, density structure in the wind or something like that. Shouldn't you also see it in the other diagnostics? Has there been any attempts? I mean, you should then be able to trace that in UV and in optical in the basic mass loss.
Yeah. So this is definitely something that we've been looking at. There are some difficulties though. So if you take zeta pup specifically, what you find is that the UV profiles, at least for carbon-4, are very saturated. And so if you actually model a change in the mass loss rate of that magnitude, you find that it's actually not trivial to detect. You might be just at the edge of detecting it, but it would be kind of a very small effect. So maybe some other stars would be better suited to UV in this case. And then when it comes to stuff like H alpha, for instance, the biggest difficulty with H alpha comes from, you'll have all sorts of archival data from different instruments, and sometimes the normalization can be quite challenging. And so getting really good data sets and being able to account for the systematics is actually a really tough job. And I think there are some efforts that are ongoing in this direction, and hopefully we might see some results at some point, but it's just something that's a little bit hard to do. So I agree with you. I think that this is something we need to consider over a whole range of diagnostics, and maybe that just means that moving forward, we need to be a bit thoughtful of these new timescales when assembling time series.
Agreed. And perhaps also look at some unsaturated UV lines. I mean, Fuse was quite a while ago, so you could look at the phosphorus lines and stuff like that, right? Which are also in theta Puppis unsaturated, right? But like you said, more generally, to look at other mass loss diagnostics over these timescales, we just dig into a couple.
Absolutely.
Because if there are these type of big changes, as indicated by X-ray data, you should see it in a bunch of diagnostics, actually. An average, as you say.
Yeah, completely agreed, and it's definitely something that we're kind of moving forward towards. So yeah.
All right, thanks.
Yeah, thank you. All right, so
Okay,
moving
let's
on
go for
to part two. So part two is maybe what you've been more used to hearing me talk about in the last few years. I apologize if this is not the first time you hear this. But I'll very quickly provide an introduction to massive star magnetism. I know that by now, most of you are probably at least somewhat familiar with it. So first off, how do we measure it? We use the Zeeman effect. We know that in the presence of an external magnetic field, we lift the degeneracy on the magnetic quantum number, and we create splitting in atomic levels, which then creates splitting in line profiles. So this can be seen in sharp line stars. So for instance, in slowly rotating A stars, you can actually see the splitting in the total intensity spectrum, which is really quite incredible. But in the case of more massive stars, of course, they typically rotate faster. They also have microturbulent broadening. There's all sorts of things going on, and so it's much harder to try. The Zeeman split is going to be smaller than the actual broadening of the lines. And so in that case, we need to rely on spectropolarimetry. So this is an example of high resolution spectropolarimetry. On the top, we have some sort of null profile, which is created by combining beams that should cancel any astrophysical signal. This is just a sanity check to make sure that we don't have any spurious signals. On the middle panel, we've got the Stokes V. So this is the circular polarization profile, which is indicative of the presence of a magnetic field. So when we have our Zeeman splitting, we expect delta M of plus and minus 1 to give opposite circular polarization signals, and so therefore by subtracting those, you get these kind of characteristic wiggles in the line profile. And in this case, this was a kind of a later type star. So this, I think, was a late B type star. So you actually also see spots. So in this part of the talk, I will extend a little bit my definition of massive stars to include the intermediate mass stars in some cases. So I do apologize for that. So this is what we're seeing. We're seeing a spotted star which creates this bump in the line profile. But we're also seeing, kind of the magnetic field in circular polarization. Okay, why do we care? So I kind of lied earlier when I said I wouldn't talk about compact objects and such to justify what we do, because still within the massive star community, I think that the magnetic massive star community remains a little bit more marginal, and so in particular, we like to think a little bit about kind of the evolutionary consequences of magnetic field, which I'll cover in a second. The basic idea is that you can potentially create much more massive remnants and massive late stages of the star. And so we think that, galactic magnetic stars might actually be the precursors of parent stability supernovae, magnetars, and also the type of heavy stellar mass black holes whose coalescence was observed by LIGO. So of course, this was kind of the first detection of a black hole merger, which was inferred to have, the black holes were 36 and 29 solar masses, which is extremely hard to reproduce with single star evolution at Milky Way metallicities, because the mass loss is too high and you just basically lose too much material to be able to form such massive black holes. Okay, so let me just provide you with a quick overview of a whole host of large surveys. So really very involved observing efforts that involved, in particular, to look at the interaction with binarity. There was the Bynamics collaboration, LIFE, to look at kind of later evolution of these stars, and then there was also a few here, but that's the gist of it. So this is very intensive observationally. Sorry, I'm going in the wrong direction. And what is the general picture that these surveys have painted for us? Well, first of all, about 10% or less of all OBA stars exhibit detectable surface magnetic fields. And I'd like to focus on the the surface part here, because as we know, the convective core could actually produce its own magnetic fields, but those would be kind of buried in the star and potentially never make it to the surface. However, there are some recent results on the astroseismology of red giants that have kind of shown that you can infer the presence of magnetic fields from the cores, and there's a whole research line that's dedicated to that now, which I won't focus on here, but is actually quite interesting in its own right, and really something very promising. Now, these surface fields appear to have properties that are mostly decorrelated from the actual stellar properties. So unlike low mass stars, where you'll have a very important dependence on rotation, for instance, or the mass of the star in terms of how the fields or the magnetism presents, this is not the case for OBA stars across 2 decades of stellar mass. So this is quite remarkable. The fields are strong, of order a few kilogauss, typically have a relatively simple topology. So we're talking about a large-scale dipole, and they are stable over long timescales. So we've observed some of these stars for years or even decades and haven't seen any large-scale changes in the fields of those stars. Okay, now for the more massive stars, the OB stars, which we're all interested in, they have a really important effect on the wind. So because the wind is ionized, you can expect that the magnetic field will channel and eventually confine the wind material. The whole thing is basically a competition between the magnetic field and the wind. So you have this basic structure here. So we have what we call the Alfvén radius, which is the radius where you more or less balance out the wind kinetic energy density and the magnetic energy density. And so basically beyond that radius, you're able to break apart loops of magnetic field. But within that radius, you actually have closed loops, which means that the material that's launched inside of those loops actually remains confined. And so in this scenario, we have what we call a dynamical magnetosphere. You've got material that's being launched from both magnetic hemispheres, comes and meets at the magnetic equator, shocks, cools down, and eventually falls back to the surface. This can lead to all sorts of variability in many different wave bands. So for instance, the strong shocks that occur along the magnetic equator will lead to very strong X-ray emission. The very dense confined region here also gives rise to H-alpha emission. And then the important thing to note is that the magnetic field axis is not generally aligned with rotation, which means that over the course of a rotation period, you will be viewing the magnetosphere from a varying angle, which means that you should expect a lot of these diagnostics to be rotationally modulated. Now, I won't go into too much detail here, but if you have rapid rotation, you might actually be able to centrifugally support some of the material into a dense cloud, into what we call a centrifugal magnetosphere. So there are different kind of phenomenologies attached to these stars and their magnetospheres. If you want some more details, please ask me about it after the talk. Now, the effect on magnetism, the effect of magnetism on the evolution of the stars can be quite important. So as I said, the magnetic field can confine the wind material, which then crashes back to the surface. So overall, you're actually reducing the effective mass loss rate of the star. And so on the left, we're seeing kind of evolutionary tracks of stars based on their field strength. So we've got stars that are initially at 80, 60, and 40 solar masses. The changes are most dramatic for the 80 solar mass star, so I'm going to focus on this one. So each of the dashed lines here corresponds to a different field strength, with the strongest field strength being the darkest one. And so as you can see, if you don't have a magnetic field, you end up losing maybe almost half of your mass over the main sequence lifetime, but you can reduce that by a significant fraction if you introduce a strong magnetic field. Now, another important effect is that the magnetic field very efficiently spins down the surface of the star. In this case, once again, we're seeing the rotational velocity that's divided by the initial rotational velocity. So basically just seeing how the rotational velocity changes with fractional main sequence age. And depending on the prescription of internal angular momentum transport, you get very efficient spin down that can occur either really, really quickly on the main sequence or occur throughout kind of the lifetime of the star. Oh no, sorry. All the dashed ones are non-magnetic. So a non-magnetic star would spin down, but on a much slower time scale. So sorry, it's between the dotted and the full lines. That depends on the actual prescription. But if you have a strong magnetic field on a massive star that has a very strong wind, you spin down within about 20% of the main sequence lifetime. There's actually some empirical evidence of spin down. So these are observations for the star Sigma Ori E, which is an early B-type magnetic star. And observations taken from the 70s up to about the 2010 show that, in fact, you can do some timing with some light curve features. And here you see the O minus C diagram, and you can see that there is a quadratic term, which leads us to infer a change of 77 milliseconds per year. So basically, that's the spin down of the surface. And so this is kind of a really nice empirical validation of this idea. Now, there are several open questions in the fields of massive star magnetism. So regarding the origin, I'm going to blast through these slides a bit quickly because I realize that I'm kind of running out of time, and I do want to focus a little bit on some other things before we move on to questions. But we don't know how these magnetic fields form, which means that we don't actually know how massive stars form. And this is actually a really important point that, even though we only think, 10% is not so important, well, there's something fundamentally missing in our picture of massive star formation. So there are a few different ideas. This also relates to the subsurface convection zone. You might ask about it in the questions. We also aren't sure if how the fields themselves evolve over time. So there might be some ohmic dissipation. We're not quite sure yet. There are many different diagnostics, and as I said, a lot of those are going to be rotationally modulated. So here on the left, we have a light curve of a magnetic star. Actually, this star was discovered to be magnetic because of its light curve. We got some follow-up spectropolarimetric observations and actually detected the field. So you can see this very nice periodic variation in the optical light curve. So other diagnostics include H-alpha. Once again, I won't go into too much detail about this. And also the UV line profiles, the UV resonance light profiles. So because they're so sensitive to the wind, if you have a large-scale magnetosphere, you expect to see changes in the UV line profiles, but also kind of atypical line profiles because of the very complex and unique velocity and density structure of these winds. And so here you have on the top and bottom the silicon-4 and carbon-4 doublets for two normal non-magnetic O stars. And in the middle, you have the most strongly magnetized O star, NGC 1624-2. And you can see not only very strong variability between two different observations, but also very important qualitative differences between the line profiles of -2 and these stars with similar spectral types. And there are some early theoretical line profiles that can be eventually fit to this to try to understand how we're viewing the magnetosphere. Okay, so I want to spend a minute or two talking about the Mobster collaboration. So this is magnetic OBA stars with TESS probing their evolutionary and rotational properties. Sergio actually nicely introduced this earlier on, so I won't spend too much time on it. But there are a few results where, for instance, we show the variety of periodic variations that we see in the light curves of magnetic stars. You can ask me about this in the questions. This I will highlight very quickly. This is a binary that we found where it's an eclipsing binary. There's also some pulsations that are present in the light curve, and there's also some rotational modulation, which led us to realize that one of the stars was magnetic. It turns out that the other one isn't, and they're a fairly close binary, a young binary that's circularized. And so some of the origin hypotheses for magnetic fields involve mergers, but this is very, very difficult to reconcile with such a scenario. So right now we're conducting a population study of OBA stars. So we want to look for rotational modulation signals in bright OBA stars that have been observed with TESS. compare the properties of the general population to that of the subpopulation of known magnetic stars, and eventually use that to refine search criteria to select high probability magnetic candidates by increasing our number of known magnetic stars, especially at the higher mass range. So there's only 12 known magnetic O stars. We will have a better chance to answer some of the big open questions that we have in stellar magnetism. So this was work that I did with some summer interns at Goddard. So I just wanted to highlight their contribution. And so this is the basic project. Once again, I won't go through this into too much detail because I do realize we're running out of time. But there's some important considerations about the data reduction and the data detrending. So this is something that we're working very strongly on trying to figure out well so that we can automate it for a large number of stars. We do run into some issues because there's many varied subphenomenologies that are seen among magnetic OBA stars. So we have to be able to account for all of those. But there's also some important confounding signals. So for instance, binaries is an important one. Pulsations could also be one as well. And we want to figure out the systematics that are related to that when we're trying to put together a magnetic sample. So I'm going to quickly transition to part 3, which is the shortest part of my talk. And it's a bit of a wish list. So what would we want to be able to pursue this work? So I just mentioned that we're putting together a list of stars that show rotational modulation signals or potential rotational modulation signals in their light curves. Well, we'd like to follow them up with spectra and eventually spectropolarimetry. So this will allow us to say something about how binarity might contaminate some of this sample. We also want to basically characterize those stars, and eventually we can have a really high yield sample of stars that can be further followed up with spectropolarimetry. I also want to talk very quickly about ultraviolet because we are facing a potential gap. Hubble, is still going strong, thankfully, but who knows for how long. And of course, there's very large missions like LUVOIR, which are planned. But in the meantime, it's kind of unclear how we'll get spectroscopic data in the ultraviolet, and even more so spectroscopic time series, because of course an observatory like LUVOIR is going to be extremely oversubscribed, and it's not particularly suitable to the type of follow-up that we need to really understand the variability that characterizes the winds of these stars. There's an important thing to be said about cadence versus baseline. So because we have a very, very long range of variability, so from minutes and hours to years and decades and perhaps even beyond, we do want to think very carefully about having an agile suite of multi-wavelength instruments that allows us to resolve temporally these stars on the shortest timescales as well as the longest ones. And one thing to keep in mind is that the upcoming suite of very large telescopes is obviously great because it's something that will allow us to do tremendous things. But sometimes the name of the game is small but mighty, and especially because our stars, at least in the galactic setting, are very bright, there's a lot of things that can be done with smaller projects, and this is something we should think about as a community. And with that, I will thank you all and take any questions with the small remaining time. I'm sorry for going a bit over.
Okay, thank you very much, Alex. No, sorry at all, because the idea of this seminar is that people can really explain things properly, not like when we go to conferences. So it was perfect, the time you needed, and it's clear that you have many other things that you want to tell to the community. So I'm sure people will also contact you for other questions. So I remember in Lacturo, you were doing very careful work in making sure that everybody were writing the questions for the proceeding. So now, right. Today you can relax and all the questions will be for you. So just enjoy the question by the people. So if there is anyone, just please raise your hand. If not, in the meanwhile, I can say that, well, we have Joe. So please, Joe, go ahead.
Oh, can you hear me?
Yep.
Yes.
Okay, so thanks, Alessandra. We have just seen recently for this nice, very nice overview. I have maybe a very stupid question, but maybe I'm getting old and forgetting something. You mentioned in your second part on the magnetic fields that more or less you stated it as a matter of fact that these stars should display or should possess a dipole magnetic field. I always thought actually that this is more or less a wishful assumption, and one of the only stars where this has been checked or could be checked, Tau Scorpii, there was no dipole at all. Can you tell us a bit about the probability of real dipoles?
Of course. So yeah, thanks. That's a really important point, and not at all stupid. Basically, you're right. I think that the dipole approximation is kind of the simplest thing we can think of, and often it's kind of convenient because obviously spectropolarimetry is quite photon hungry, and it's not something that's super easy to do. However, so you're right. TauSCO does show a anomalously complex field compared to other stars that have been observed, and one might think it has to do with just a better characterization. But in fact, in cases where more observations were taken where you were able to do, for instance, Zeeman Doppler imaging, or in cases where also there was some additional information that was obtained from linear polarization, so the Stokes Q and U parameters, you actually find that in general, you will get small departures from a dipolar field, as you might expect. So you might have kind of a slightly off-center dipole or something like that. You'll have a bit of a quadrupolar component, but in general, most of the magnetic energy is found in the dipolar component. So it's not just a useful approximation. I mean, it definitely is. But as we're finding more and more, it seems to be a pretty good description of what's going on for most of these stars. But you're right, there are some outliers. TauSCO is definitely one. On the lower mass end of things, HD 37776 is actually even more complex than TauSCO in its field. So there are some counterexamples. There are also some general questions about how this relates to the evolution of these fields. And it could be that, in a scenario where you invoke ohmic dissipation, you would expect more complex fields to be associated maybe with younger stars because the timescales for dissipation are much shorter for higher order multipolar components. So these are kind of open questions, but I think that in general, the picture that these fields are simple generally holds.
Okay, thanks a lot.
Sure thing.
Okay, we have a question here by Senk Kayan that the microphone is not working. Do you have a criterion to distinguish or determine magnetic fields and spots and pulsation in the light curve? Or do you proceed through the spectra of the star and then interpret the light curve that way?
Yeah, so I kind of blasted a bit quickly on this, so thanks for asking. So right now our general criterion, so just for all stars to look at rotational modulation is twofold. So we look at signals that, of course, can be compatible with rotation. So across the whole range of OBA stars, our general criterion, which we might refine to be mass dependent later on, is that we have a fundamental frequency that's under 3 cycles per day. Because above 3 cycles per day, of course, you're breaking up the star. So that doesn't work. And of course, for O stars, it should actually be lower. Now, the second thing is we're usually looking for a first harmonic. This is a fairly widespread criterion, I think, in terms of dealing with rotational modulation. But it has to do with the fact that pulsations typically are maybe a bit more sinusoidal. So this is one way to not get too contaminated by pulsations. But of course, once again, you do have some other confounding factors such as eclipsing binaries. So a lot of the work also happens downstream. So you identify the stars which you think have rotational modulation that are strong candidates because they show, this clear, periodic, repeatable behavior. But then you actually want to refine that through literature searches. So if you do have, a known binary whose orbital period corresponds to the period of variability that you're observing, then this is one that you might want to set aside. But of course, you're right. It's not going to be perfect. And that's why we need some additional information in order to try to really weed out as much contaminants as we can and really focus on magnetic candidates.
So before jumping to the next question, I wanted to say that soon there are 2 surveys of galactic massive stars, or including galactic massive stars, that will be starting. One is WIF and the other is Formos. And I think this is going to be great because at the moment we have like 40,000 OB star candidates. And even if only half of them are finally OB stars. This will mean a lot of stars that were before uncovered, and then we can really go to the test-like curves and check, no? Because with the spectra, you cannot say if this is a OB star. So I'm sure you know, but it's something interesting for the community also. Okay, so now we have John and Huip. So John, please, June.
Yeah, I'll ask another question then. So you said something there which was very interesting, because I was under the impression that sort of, you know, community, say as you wish, has sort of started to converge on the merger hypothesis for these magnetic fields to be like the leading hypothesis, presumably because it gives the incidence rate a very natural explanation, right? But you said something just in passing that this is very difficult to reconcile with some results that you have, but you didn't really explain. Could you perhaps explain what those results were? Because I couldn't really understand what you meant.
Yeah, sure thing. And yeah, thanks for pointing that out. I do agree that the merger scenario, I think, is really gaining traction over the last few years. Let me just pull up that. Yeah, so the basic idea is that we have this fairly close binary of young B-type stars. Okay, the mass ratio is very near to 1, so they're essentially identical, and the orbit is circularized.
Right.
So one of them is magnetic and the other one isn't.
Okay.
So if it had started as a hierarchical triple, you would not expect the orbital parameters you have today at such a young age. It's very difficult to reconcile with its evolutionary state. Now, this is one case, but there's obviously also other cases that are even more challenging to reconcile. The most obvious one being epsilon Nupi, which is the only known massive close binary with 2 magnetic components. So in this case, you know, it's even harder to try to imagine a scenario where both of them were formed by mergers. Now, this is not to say that the merger scenario is not valid, and I think that there's still a lot of work that needs to go into evaluating it. It turns out, actually, I'll mention in passing that with Sergio, we were just talking before the seminar started about the fact that I just came back from the MIAP program that's currently going on stellar magnetism, and merger scenario was actually a big discussion over there. And I think that's one of the things we want to keep in mind is that, you know, it is quite possibly a viable process to form magnetic fields in massive stars, but it doesn't have to be the only one. And I think that, you know, there's some other lines of evidence, for instance, the fact that you do have some pre-main sequence stars that are found to be magnetic, that can be hard to reconcile with that as well. But, you know,
well, to be honest, this seems more hard to reconcile, actually. I wasn't really aware of this result. I think you might, and this is published, I guess, by Matt.
Yeah. So there's some work by Alessian and collaborators on this. The other thing I'll mention too is
should address this, because I agree. Just hearing your argument now, I agree. This seems like an
and it has. I think it's just that maybe there's a scenario that's gaining more traction nowadays, but I think it's just important to keep a view of the different possibilities. The other thing I'll mention very quickly is that the fact that the incidence rate appears to be flat across OBA stars is also something that's a bit difficult to reconcile with the merger scenario, because the multiplicity fraction should go down as a function of stellar mass. So that's another thing to keep in mind. But once again, it's not to discredit the merger scenario, and I think that it can be a very important channel towards stellar magnetism.
Yeah, right. Very diplomatic.
Okay, Huip, please go ahead.
Hi, Alex. Thank you so much for your very nice presentation and summary. I had a question about the space photometry that you showed in the first part of your talk. You showed a slide with all kinds of, well, it was not clear to me whether you were stating it was periodic or not, and then whether you had a correlation with X-ray, this one. And next one, I mean, was there a periodicity in this signal? I didn't think so. But the next slide suggested that you model it, and which was strictly periodic, which is confusing.
Okay, so let's start with this one. So first of all, you're right. There was not a specific periodicity that was found, but rather a characteristic timescale. And so I think that the work that Tahina did on this is consistent with the view of a cyclical variability. The same can also be extended to his 2018 work on Zeta Pup, which he did with Bright, where he actually uses matrix light curve inversion to try to map the surface, and he can recover kind of more or less stable, spot configurations for roughly something like 20 rotational cycles. And so, over time, you can see that the spots seem to drift on the surface. If you believe that these are brightness spots on the surface, of course, once again, we need to be a bit careful with the interpretation here. But basically, the idea is that, you would have something that's stable on the order of several to maybe a few tens of rotational cycles and slowly changes over time. But what we're seeing in the light curve here seems to also support this picture. Now, this simulation, of course, this only has like static spots on the surface because we were just trying to reproduce the character and the evolution of the DAX throughout the velocity space. So we were not looking at trying to vary, the position of the spots and do some sort of long-term time series of observations. This is really just to try to see, can we take the photometric amplitude that we see in the light curve, associate that to kind of realistic spot characteristics, and then from that, can we extrapolate wind structures that lead to synthetic UV profiles that look like what we see in real observations? And the answer is yes, basically.
Okay. Your next slide, the X-ray modulation, is that related to this one?
So this one is Xi Persei, so yeah, it's the same star. Yeah.
Yeah, but that is the same model as how you model the discrete absorption components in your model?
So this is not really modeled yet.
Okay, good.
Yeah. I mean, I there's the little toy model here where we look at just absorption, but it's not thoroughly modeled. This is something that we're currently working on.
Thank you very much.
Yeah, sure thing. Thank you. Good to see you.
Yeah, same here.
Okay, Gonzalo, we have the last question then.
Hi, can you hear me?
Yes.
Yeah, very nice talk, guys. I just want to say thanks to point out that we can do things with the smaller telescopes. We are trying to do that, finding new magnetic candidates. And some question that people usually ask me. So finding these new massive candidates, magnetic candidates, just help in any way to any of the scenarios, as you say, with the possibility that the merger scenario is not helping, that kind of thing.
Yeah, so honestly, I think there's a danger, and maybe earlier in my career I was a bit naive and always saying like, oh, more is better. But you're right, I think we need to have kind of a clear picture of what we can do with more. So there's a few different directions that we can go in. So first of all, I think you're right that discovering specific objects that challenge some of the scenarios that we have currently is an important thing, and we're going to find more and more of those, which will paint a picture of which channels are possible and what their relative contribution can be. So this is obviously one important thing, I think, moving forward. And so that's also why, like I mentioned very quickly that we would eliminate binaries that have orbital periods that are exactly the variation that we see, but we don't want to eliminate those that have different orbital periods, for the simple reason that actually magnetic stars and binaries are really interesting and really important. But the other thing too is I think that there are also portions of the HR diagram and the evolutionary tracks that we want to better fill out with magnetic stars. And so in particular, it's quite well known, and there's a specific collaboration addressing that, the LIFE collaboration, but there is a dearth of magnetic evolved stars that are known. So this is something that we would want to fill out more so that we can really track the evolution of the field and the star as a result of the field being there. once again, it's also dependent on the mass bin, right? I think at the highest masses, well, you can make a really strong case that, you know, even finding one or two more stars would actually be significant, because we don't have that many. We have on order 12 magnetic O stars, and they all have kind of their own peculiarities. So drawing a consistent picture of all of them is a bit of a challenge. And so just in that case, adding a few more is actually a very valuable contribution. So it's a very kind of multifaceted and tailored question depending on what you're specifically interested in. But I think that there's many ways in which that can help us improve the bigger picture. And I think you're right that it's important to focus on that downstream.
Okay, well, yeah, thank you. What I usually answer is important, but we are difficult in the soup. Yeah, it's important.
Yeah. And you know, of course, you might be one of those people that I omitted slightly in terms of you know, interesting and important projects going on that are also very synergistic with that. So I do apologize for that, but yeah, thank you so much for your efforts, Gonzalo.
Thank you.
Okay, so this was the last question, and related to that, I wanted to also ask you, because you were writing a wishing list. So in terms of number, what would be the number of magnetic stars above, let's say, 15 solar masses that you would like to have in the next 5 years? Because this will probably happen. The statistics are going to increase. So 50 would be enough, or you would like to have 100? At some point, it's not possible to have too many because of this 10%. So with what number you have the impression that things will begin to be the puzzle, you have enough pieces to build an interesting puzzle there?
So one thing I'll mention, so I mean, if we were able to double it, it would be tremendous. And it sounds like it would be trivial to do so, but there's one thing that I kind of conveniently swept under the rug, is that it's going to be actually very hard to detect the more massive ones for a couple of reasons. First of all, the rotational modulation, you know, for lower mass stars, so if you start like kind of B2 down to the AP stars, a lot of the actual photometric variation is due to spots and is relatively high amplitude and easy to detect. However, when you're talking about stars with very strong winds that cannot form surface abundant spots, you're actually purely dominated by a varying column density due to a varying angle of your view of the magnetosphere. And this is a relatively subtle effect. And so here we have an example of the star HG 148937, for which James Barron did a really, really nice analysis. And he does recover the rotation period, which we know from magnetic measurements to be about 7 days. And he recovers it in the photometry, but you can look at the actual amplitude here, and it's on the order of 2 millimags. I mean, it's really, really small. The other thing too is that we mentioned that these stars have dynamic magnetospheres. There's flows that rise, then fall back to the star, which adds a bunch of stochastic signal to the light curve that is actually something that we're trying to characterize moving forward. So that's kind of another project that I haven't talked about, but we need to understand what are the other signals that arise in the light curve. Now, finally, the most important difficulty with these stars is that because of the very strong interaction between the wind and the magnetic field, as I mentioned earlier, the surface rotation breaks very, very efficiently, which means that the rotation periods are typically longer than the current length of a test light curve, for instance. You know, most of these stars are observed for a single sector, which means 27.4 days. But we know that, you know, NGC 1624-2 is on the order of 150 days. We've got, on the extreme side of things, HG 108, which is 55 years. So, you know, you can't observe the rotational modulation from a lot of these stars, which obviously kind of limits our detection quite a bit. So the 10% is, you know, what you would expect for most stars. You might reduce that by some factor due to, you know, all sorts of spurious things. Maybe the inclination angle is not right. Maybe they have very long periods. From what we're finding from our initial efforts on the population study, you would expect, at least on the lower mass end, to recover 70% of rotational modulation in the stars that are known to be magnetic. But on the higher mass side, it's actually going to be much smaller than that. So, you know, if we can double it, it would be tremendous. But let's see what happens. Then
also, if I understand properly, having this test and spectroscopy does not mean that spectropolarimetry is not needed anymore. So it's important to
No, of
also
course not. Yeah.
go
Yeah.
ahead with that, because there will be another maybe easy way to detect other candidates that are not obvious from this, no?
Absolutely, but unbiased spectropolarimetric surveys are not efficient anymore, because in terms of completeness for, you know, stars for which we can do this, at least for the O stars, we're pretty close to 100%, right? Like we've observed a lot of them, not 100%. You know, there's still some real estate, but it's not as efficient as it could be, for sure.
Okay, so let's see what happens when we will talk in 10 years.
That's right.
Thank you very much, Alice, and thank you everybody for joining. The recorded version will be in YouTube, and I will send the mail soon. So if you want to go back to some of the details, it will be there. And next month we'll have a different talk. So it will be Nick Wright, who will be giving a review. He's more senior, will be giving a review about the OB associations. So I hope to see you all there, and take care with the driving, Alex.